Okay, so Andy and I had a conversation about how to move forward with some of the different stuff to address student concerns and to address just stuff that's hard. One of the things we're going to do is actually post numerical solutions to, or answers to the problems so that you can know whether you're doing them right. But it'll be the solutions that are graded. We'll have more as we go here on that too. But for tonight, let's go ahead and if we're ready to get started with presentations, Andy, are you connected and ready to drive, or? All right. Well, so in the absence of Andy, who's ready to present? I know we have a few people ready to present.
Yeah.
Who'd like to go first?
Mike, Mike, I did have a list in the announcements. We could do it in that order, or whoever wants to go first.
Okay.
But
Let's
if
do
you can change presenters, I'm sorry.
Yep. Let's see. So Jamie was up first, I think. So Jamie, are you ready to present? Jamie, are you here? Okay, I don't see Jamie in the list of attendees. So why don't we go to Brett? Are you ready to go, Brett?
Sure.
All right, let's see if I can figure out this new interface. Make presenter. Okay, you should have presenter privileges.
Okay, is my screen is showing now?
Yes.
No? Okay, yes, okay. Okay, so Andy wanted me to present on question 3.34, which I've got pulled up here in R and my R Markdown file. So I think something that Andy wanted me to highlight was my usage of R, which obviously after, last term in the summer session I'm a little more comfortable with. So for those who are unfamiliar, R Markdown lets you write in LaTeX in combination with just writing R code and executing it by segment, and it really does produce a nice looking document that can get your information across. So the question revolved around Hoover and Glue and the number of no-hitter baseball games and creating a kind of a prediction and comparing that to the actual results. So this right here is the LaTeX code for the math that you see here. So it's just got a bunch of fractions multiplying because I used basically found the average through weighting. Taking 0 games, 18. So there were 104 total games, and I found the value through multiplying how many games there were for each value. And then all I did was create a function here that simulated a Poisson distribution using, so it takes in a k and a lambda, and it returns the exponential function with -1 times lambda, and multiplies that by lambda to the k, and all that's divided by factorial k. So that's just what the code looks like to reproduce that function. And then I fed in the number of games, 0 through 7, and the actual amount of seasons that had, that many no-hitter games. And then I took the value from this original function here, the 205 out of 104, and I set that as my lambda. And then what I did is I used the sapply function. So if you guys are unfamiliar, the apply functions allow you to do vectorized operations in R, which are a lot more expedient and a lot less likely to get Andy to make fun of you for using a for loop or something like that, which is, I think, what most people are comfortable with. But it's not the R way, as we've been taught. So the sapply function allows you to take and apply a function of your choosing to a data frame or a vector or what have you. So in this case, I have the number of games vector here, and I apply the Poisson distribution that I made here, and multiplied it back out by the 104. and then what I did is I rounded it because I didn't, you can see in the actual result I have the expected seasons here, but I also have the rounded seasons because it doesn't make much sense to estimate that there are 14.48 seasons because where you have X amount of no-hitters, because that doesn't make any sense in real-world terms. And then all I did is so you can obviously in R you can do vectorized operations. You can just subtract vectors from each other with no looping, nothing complicated like that. And then I did a column bind here, which just binds all these columns together into one data frame, and then I outputted it here, and that's what you're seeing in the code right here. If I had set this wider, you would actually see all of these as columns in a row instead of one set of columns here and another set of columns here.
Hey, Bruce, can you please make the code page wider for just a minute, because I cannot see very well on the, because you have two pages at the same time, if you don't mind. I mean, the other page, the code page.
Oh, the R. Well, I mean, this is the code right here.
Okay.
So
okay.
the R Markdown document allows you to have the code, and you can set that either so that it's visible or not visible. And then from there you can see the execution of the code. But this is the code. This is exactly what you were seeing on in the R. Yeah.
All right, thank you.
No problem.
That looks better now. Thank you.
Yep. So I don't know if anyone else has any other questions.
Brett, Shaker here. I mean, I think you can use the built-in function depoise or something like that. I mean, is there any specific reason for writing your own function there?
I think my goal is just to demonstrate that I understood the function. Obviously, there's built-in functions for basically everything we're going to do in this course. So I just assumed that I was kind of building my own from scratch, because otherwise it would just be just putting numbers into our functions, and I personally didn't interpret that as the intention of the course.
Okay, fine. Thank you.
But I can't speak for anybody else on that. Well, okay. If no one else has any other questions, I think I can turn it back over to Mike if I can figure out how to do that.
I'll take it. So James, are you ready to go?
Brett, that was great. Thank you. And for the 607 students, remember Brett is has 4 full courses under his belt and is taking 4 more. So hang in there. You'll be writing code like this real soon now.
Yeah, I was pretty lost as well last term, so I definitely get where a lot of the people are coming from.
I actually have a question.
Sure.
This is Jim. So the weight, can you go back to the weighted average? So when I calculated lambda, I did the total number of no hitters divided by the total number of seasons. Why is that wrong?
What makes you think it's wrong?
Well, I guess just having seen this this method is is there some subjectiveness here, or what is?
I believe if you're doing what I think you're describing, you get mathematically an identical result. And
yeah, I just left it as a fraction here, but yeah, you would get exactly the same thing, I think.
And the reason for that is that they all have the same denominator of 104.
Okay. Okay.
Yeah, so it would work out exactly the same if you just did 0 times 18 plus 1 times 30 plus and all of that divided by 104. You would get exactly the same thing.
Right. Okay. Got it. Okay.
Okay.
All right. Any other questions for Brett? That really is quite good. Okay, James, I'm going to make you presenter.
Okay.
And so James is presenting 3.16.
Okay. So this is the problem that wants you to find the probability of different poker hands. I volunteered just to do this because I like playing poker and have managed to win a few games without knowing how to do this. But it was actually pretty fun because this was something that I thought about before. The basic pattern, once you figure it out, really helps figuring, the subsequent hands. And so the basic pattern is you choose the rank, then you multiply it by choosing this when you choose the suit, and then you divide by the odds of, or you divide by the total number of hands. And so the total number of hands, if you're dealing out 5 cards like in poker, is 52 cards in the deck, and you're dealing out 5 of them. So we come down here, that denominator for really every single hand is going to be this 2,598,960. And then this top part, for a lot of them, you just end up figuring out the combination that chooses the rank, so ace, 2, 3, 4, and then choosing the suit, so one of the 4 suits. I guess we'll just start off with the probability of the straight flush. The way that I did this was first to just chart out all the different straights based on rank. And so in poker, you start with ace, and then you pick 5 cards all the way up to 5. And it turns out that we have 10 of these. I included the royal flush as a subset of the straight flushes, but I know that could be debatable. So we have a total of 10 different straight flushes, and we have one of those for each suit. So one for diamonds, clubs, spades, and hearts. That means that there are 40 total straight flushes out of the 2.5 million plus possible hands. And that leads us to the probability of 1.5 times 10 to the negative 5. Okay. I'm going to go ahead and check the chat here, see if that's... Okay. So that's a straight flush. And I guess now that I think about it, it didn't really conform to the pattern that I had found. But the rest of them really do. So 4 of a kind is a hand where we have the rank matched in 4 different cards. And then we have this kind of last slot, this 5th card that really doesn't matter. So the probability of 4 of a kind we find by choosing first the card's rank. So there's 13 different ranks, ace through king. And then we choose one of them. And so this is kind of setting the rank. And then we choose the suit. And that is, let's see, because there's 4 of a kind, it's 4 choose 4. And then finally, that anything else, this is whatever is whatever card that falls in that slot is we've already made the hand over here. That means that there's 48 cards left, and we're going to pick one of them. So that comes out to 624 different combinations over that 2.6 million, and that leads to a probability of 2.4 times 10 to the negative 4. This pattern kind of repeats for full house. You can see we pick again, we set the rank, and then we set one of the suits, and then for the last 2, we set the rank again, and then we choose another suit. And I guess, just if you played poker, you know this, but gradually the probabilities increase. And so, when you're playing the game, the least probable hands beat the more probable ones. So I've played a lot of hands, and I don't recall ever getting a straight flush or a four of a kind. No, I haven't had them, but I've seen them. If there's any particular ones people want to go through, I'll do my best to explain them. Because I actually found when doing this that they got more complicated as they went down. So the problem straight was one that I found pretty confusing. But go ahead.
No, I'm interested in the three of a kind. That's where I had a little struggle.
Yeah. So, yeah, three of a kind, I guess just kind of based on the pattern would be you set the rank as choosing any of the 13 ranks, and then you set the suit by of the four suits, you choose three. And I think, the way conceptually you choose three because you need to have because you've already chose one, you can't choose four in this case, right? Like by definition, it needs to be a different suit. And this is choosing the pair. I'm sorry. Yeah, now my memory on this one's getting tripped up. So 4, choose 1.
Well, actually, the way that I did it, I can probably tell, and I don't know why I'm getting it wrong. Somebody can explain why it is. So here's how I have approached it. So the three of a kind is 3 having the same face value, right? Which means 4 of 3. So I have for each, there are 4 suits, and you have to choose 3 cards, so that makes 4 of 3. And obviously you have 13 cards to choose from, 13 different face values. So the first 2 multiplication absolutely makes sense to me. However, the last 2 cards, which can be anything, right? Which means since I've already chosen 3 cards, the 4th card is actually 49 cards left in the deck because I've already chosen 3 cards. So it should be 49, and the next card, after chosen 1 out of 49, I have to have 48. So my calculation is 13 multiplied by 4 C3 multiplied by 49 multiplied by 48. But obviously that answer is wrong. So that's where I need help.
So one of the challenges with these problems is that you have to be careful not inadvertently to give yourself a higher hand. So if you choose any one of the remaining 49 cards, you could choose, if the first 3 cards were king, 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 if you choose any one of the remaining 49 cards, you could choose the 4th king, and you no longer have 3 of a kind, you have 4 of a kind. So you have to choose. And actually, if you look at what he's got on the screen, you'll see the middle entry there is 12, choose 2. If you chose 2 of the same card, so if you have king, 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 and then you choose 9, 9, you now don't have a 3 of a kind, you have a full house. So not only do you have to choose 2 cards of the remaining 48, but you have to make sure that they are of different face values, right? So you have to choose 2 of the remaining 12 face values, and then for that you can actually choose them from any one of the 4 suits. So that's what the 4 choose 1 and the next 4 choose 1 takes care of.
Okay, I see your point, but I still didn't understand the 12 2.
Okay, so the 12 choose 2 comes from the fact if we've got king, king, king as our first 3 cards, then we can choose 2 more cards with any face value other than king, but they can't match each other either, right? Because if they match each other, we have a full house, not 3 of a kind. So if I choose king, 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 then I could choose ace 4, I could choose 5, 7, right? But they have to be two different cards of the 12 remaining face values. So I've got to choose 2 of those 12 remaining face values. And then because we know for each of those face values there are 4 possibilities from the 4 different suits, I have to then multiply that by 4 choose 1 and 4 choose 1 again. But the 12 choose 2 comes from the fact that we have to choose 2 different face values of the remaining 12. I can't choose 2 of the same.
Okay, so let me understand this. So the first of the 3 cards is 13 4 by 3. That's fine. So if I choose king, K hearts, K spade, and K club, so I should not be choosing K dice. So
right.
That's the reason you cannot go 49.
That's right.
Okay, so this 12 is because you already chosen one king from one of the suits. Is that why you're going the 12 remaining cards?
I say that one more time.
So I still didn't understand the 12. What are the purposes?
So there are 13 face values possible, right?
Right.
You've chosen one of them for the 3 that match.
Okay.
When you draw the 4th and 5th cards, there are 12 remaining face values that you can draw from. Right? Because you can't draw from the 13th. So there are 12 remaining that you can draw from. You need to choose 2 different face values from those remaining 12. Otherwise, if you choose 2 that are the same face value, you'd have a full house. So 12 choose 2 says I need to pick 2 different face values from the remaining 12. Right? So it could be I choose a 5 and a 7 or a 3 and an 8. But I can't choose a king again, and I can't choose 2 that are the same face value. Right? Another way maybe to look at that would be I can choose any one of the remaining 48 cards, like you were saying, right? But then that last card that I draw, I don't have 47 choices again. Now I only have 44 choices, right? Because once I draw that 5 of hearts, I can't draw any of the 5s again. So now I can't draw the kings and I can't draw the 5s. So an alternative way to put this together might be to say 13 choose 1, 4 choose 3, 48 choose 1, right? And then 44 choose 1. And the math of those will come out identical. Because if you look at what 12 choose 2 is, right, it's going to be, I think I said that right. The math will actually come out the same. So there actually are other ways to write this out, but the 12 choose 2 just comes from the fact that those last 2 cards you choose can't match. Does that make sense?
One of the ways to think of it would be like an event diagram too. You want to avoid the higher hands and figure out how to do that.
Right. So think about that, and if you want to come back to it one-on-one, reach out to me, send me an email, and we can set up a time. But I think in the interest of moving on with other presentations, let's move on. So that's very good, James.
Can I just ask a really quick question?
Honey, yeah, go ahead.
Sorry. So I understand all of this, and I did this, but then when it said in the instructions to, for instance, 2 of a pair doesn't include 4 of a kind or a full house, my inclination was to subtract out then that amount of combinations. Like there were 123,000 ways to get 2 pairs, but then there were 600 ways to get 4 of a kind and 3,700 ways to get full house. And my thought was to take those out of what it was. So instead of 4.75, I ended up with like 4.58 or something.
So yeah, you'd have to be careful how you generate the complete list first. Right. So the way James has laid it out here, he takes into account that you're actually choosing two distinct face values for your pairs, right? The 13 choose 2 says these are the two face values for my pairs. The way you're describing it, you'd have to set it up a little bit differently so that you're saying I can choose any pairs that I want. It might be that they end up matching, right? And that's much harder to quantify using this notation. It's just, it can be done probably, but it's a lot harder for me to envision. How do you set up your initial pair draws?
Well, so I ended up with that. Like I ended up with 13 ways to get one pair, and then 4 choose 2 ways to choose 2 cards, and then 6 ways to get 2. I mean, I ended up with the right answer, and 44 cards left, and then choose from there. And I ended up with the 123, 552 over 52 choose 2, which was fine. But then I thought we were supposed to deduct the number of full houses, potential full houses, and 4 of a kinds, because that's the question read in parentheses does not include 4 of a kind or full house.
If you did the 11 choose 1, 4 choose 1, but you did it as a 44 choose 1,
yes.
that does that for you.
Okay.
Right? You know that that 5th card is one of those 44 remaining cards that does not make a full house.
Oh, gotcha.
If you had done 48 choose 1, then you would be including the full houses.
So I just double uncounted. Okay.
Yeah, yeah.
Thank you. Thanks, I got it.
Okay. Any other questions? Last chance.
Mike, one last question actually on this. You know, here, can we do 12C1, 12 choose 1, and from that 4C1, and then 11 choose 1, and then 4C1? Why can't we do that actually? Then we'll get a different answer. We'll get somewhere around 108K in that case. I mean,
you're still on the 2 pair?
Yes, 3 of a kind, the one which you discussed just now.
3 of a kind. Okay.
Yeah, I mean the 13C1 is we are choosing one of the 13 sets, and then we are choosing 3 of the cards from that whatever 4 cards we choose, and then from the remaining 12 sets, why can't I choose just one set 12C1 and then pick one card from that 4C1 and then choose one more set 11C1 and then 4C1? In that case, we will get 108K actually, you know, around 108K or something like that, or 109K.
Okay, so you choose 13, choose 1, and 4 choose 3 to get the 3 of a kind.
Okay, and
then 12 choose 1 to get your next face value.
Correct.
And then 4 choose 1 from that.
Correct.
Okay. And then you're going to say 11 choose 1 for your final face value.
Correct.
And 4 choose 1 to get the suit of that one.
Yeah.
Oh, James's thing disappeared. Thank you. All right, I'm trying to think that through. So this is what makes this stuff tricky, right? Is intuitively what you're describing sounds right, but
I think it's because if you choose 12 from 1 from 12 and again 1 from 11 and then suit is 4C1, that means you can choose the same suit again and again. You got me?
Yeah, but that should be okay, right? Because we're dealing with 3 of a kind. The suits of those 2 off cards shouldn't matter.
The third one is, fourth one is the same one. It's fine.
I think I'm gonna use that old standby of let me think about this one and see what I can come up with, because I mean, what James has laid out here on the paper is correct, and I'm trying to see where the problem would come up if we do the 12 choose 1, 11 choose 1
Sure.
instead of 12 choose 2.
I mean, Mike, the only thing
Oh, you
I
know
see
what?
is
They
that
come up.
that's
No, they're okay.
double.
It's mathematically it should be okay. Yeah, let me think about this one. I don't want to get it wrong and then have to correct it anyway. Let me think about this one, and I've written down what you're suggesting, and I'll figure out why that's different.
Sure. Thank you.
Hi, Mike. This is Sreeja.
Yeah, go ahead.
I have a question about the one pair. Say 13 seed 1, then 4 seed 2. How do you do the 4 seed 2?
Two pairs.
So you're in the one pair problem.
Yes.
13 choose 1 says pick the face value for the pair. 4 choose 2 says pick the 2 cards out of the 4 for that face value. Right? So if we say kings from the first 13 choose 1, we say kings. 4 choose 2 says take the hearts and the spades, kings. And then 12 choose 3 says choose 3 of the remaining face values. Of the 12 remaining face values, and then they can be any suit. So you got 3 4 choose 1s there. So that looks right. So I guess, is there more of a question than that?
Yeah, that's good.
Okay, so actually let's go back up to the 3 of a kind for a second. So to answer your question, I've got your answer now, actually. The problem with doing 12 choose 1 and then 11 choose 1 is that you are building order into the problem in a way that you're not supposed to build order in. So I think that may not make it instantly clear, but you end up with twice as many possibilities. So if you choose 9s and then 4s, you could also choose 4s and then 9s. And if you do 12 choose 1, 11 choose 1, it treats those as different outcomes. But if you do 12 choose 2, it doesn't matter whether you choose the 9 first or the 4 first. So that's why you end up with twice as many if you do it the other way, because you're treating them as 2 different outcomes even though they're the same. So you really do have to pick just any 2 of the 12 remaining. It doesn't matter what order you pick them.
Mm-hmm.
Does that make sense?
Yes, Mike.
Okay, good. So always promise you'll do it for a week from now, and then you'll figure out the answer right away is the lesson there. All right, let's move on. We do have a few other things to get to. We can spend more time on this, but for now I want to move on so other people who wanted to present get a chance to do so. And so Maurice is up next. Are you ready to go?
Yes, I am.
All right, I will make you presenter.
Okay, I'm on here, right?
I am able to see your screen. And this
All right,
is problem 3.45, is that right?
I hope so.
Okay.
The simulation of the Prussian army death from kicked by horse and mules. Right? Is that correct?
Yeah, go ahead with that.
Yeah. Anyway, yeah, that's what I have here. So this is a simulation of this scenario here, of this example of the death by horse kicks. So basically, following on, we have these parameters. This guy formulated, figure out like the Poisson distribution for this series of events. After observing 20 years worth of data, where he found 122 deaths in 10 Prussian Army Corps. And then out of the whole data set, he figured there was a lambda, an average number of deaths per year of 0.61. So that's what I'm going to try to do a simulation here. So I'm sure there are like 100 other ways of doing it, a lot of them a lot simpler than this one. Because here, one of the things that I try to do is that I try to simulate it kind of like a binomial type of distribution, so I could have like real people on a simulation. So I'll show you how this thing goes. So here I have this variable, which basically I put here my number of simulations. I'm going to do 10,000 simulations. And then, now remember, simulation and Army Corps, I'm treating those two as synonymous. So a soldier, you could read this as soldiers per corps year. So I'm going to put 10 real soldiers, or well, 10 virtual soldiers are going to go in each corps, and then I'm going to run 10,000 corps years for this simulation. Now I'm going to the total number of men standing behind horses. The total number of people in all these corps is going to be number of simulations times the number of soldiers per simulation. So this turns out to be 100,000. Total number of soldiers that span across all simulations, all these corps years. Now this is my lambda. I have the death rate per simulation or per corps year, which is 0.61. So in other words, based on the table that he figured out here, each corps year, each one of these simulations is going to have the average death rate turns out to be 0.61 people from this corps, from this corps. So that what I try to do next is try to calculate the technical death probability on a per soldier basis. Because right now it's just for the corps. Now I want to do it for each one of these 10 individuals times the 100,000, all the 100,000 soldiers that are in this corpus. So I have my numerator, I have my death rate per simulation, that's our lambda, times the number of simulations. So in total, I would expect to get, remember, we're doing 100,000 10,000 simulations. So in these 10,000 corps years, 10,000 simulations, I would expect to find 6,100 deaths. So I'm just going to divide it by the total number of men that are in that entire corpus. So this is where I divide it by 100,000. So my theoretical death probability on a per soldier basis. Remember, I'm going on a lambda that's on a per corps year, and I'm trying to turn it on the probability per soldier. And from here on, my problem just becomes a binomial problem. And then here, so I end up with a theoretical death probability of 0.061 per soldier. So let's say I just make this let's say I put I'm going to put 20 people behind on a per corps here. A little bit. So let's just go back here for a second and let me add it. So I have my theoretical death probability. I'm going to do all of my simulations. Now this is going to be one huge array where I do, it's a binomial. The length of this array is of this vector. This is a vector that has 100,000 individuals, and then with the probability that each one of them having died from a horse kick is 0.061. So if I open up these all simulations, I will find that these actually remember that we're doing, so the ones, these are soldiers that actually died. The zeros are just, this is my 100,000 soldiers that are in the grand simulation. Now this actually is divided into clusters. Like right now the whole thing is just one big huge vector, but technically A corps is a segment of 10 soldiers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, for example, in this corps, there were 0 deaths. In this other corps here, there were 0 deaths. So that's what I'm going to do later on. I'm going to go and start counting, looking at each cluster of my size of soldiers per simulation. I'm going to look in each simulation how many soldiers died in each simulation and just keep track of the number. And this is where, yes, I have to go to a for loop. I couldn't figure out another way of doing this in something more R. I couldn't figure out the R way for doing this. I'm sure the whole thing has an R way of doing it. So anyways, this is what this whole for loop is going to do. It's going to go it's going to loop through this entire vector, looking at segments of by 10, and then summing up the number of deaths in each one simulation. And then I'm just going to store that in this deaths per simulation. This is an output. These are the results of all my simulations. So if I look at this guy, these are already the totals. So this one cluster had 0 deaths. This one had 3 deaths. This one 0, 1, so on and so forth. And this is all for my 10,000 simulations. Now, and I observed a total of 6,000 deaths. Now I'm going to do the number of deaths if the theoretical, like if I was going back to a Poisson, then if I do it as a Poisson distribution, I would have expect 5,949 deaths. Again, if I keep on repeating this whole simulation, I'm going to see that these two numbers line up pretty nicely. So the second execution, so I get 6017 versus 6094, and I could keep on just going on and on and on and on, and I'm going to see that these two numbers are pretty similar, and the output is the histograms. So this is the histogram by using by using the Poisson distribution function in R with the proper parameters. I here pass the number of simulations, lambda, and then these are the breaks from the histogram. And this is on the right. I have this is the histogram of the R Poisson, the Poisson function, and this is the histogram of the other simulations. So as you can see, I have in this other convoluted simulation, I got 8,700 deaths, 87 simulations with no deaths. This is with 0 deaths, and then versus 8693. So it's they line up pretty nicely. So and that's the end of line. Yep, that's all I have. So if anyone has any questions.
So, Mauricio, I'm afraid this could sound like I'm making fun of you, and I'm not. This is an extremely complicated, detailed, convoluted way of running this simulation. It's actually quite amazing. Right. I mean, it's.
I agree with that sort of thing.
There's always the question, in these courses, what are you allowed to use and what are you not allowed to use? For instance, as you obviously know, there is a function for doing Poisson distribution random selections, right? And so, I think for purposes of the assignment, for those of you who might have just done an rPois function call to choose your sample of how many people die in each core each year, that's fine, right? So you might have had just 4 or 5 lines of code to do this. I really am intrigued by the attempt to convert a Poisson to a binomial. Use the binomial then to determine who dies and who lives, and then convert it back later. I'm a little bit worried that the results of your simulations, right? If you look at that, if you look at your histogram that's up right there, about 87% or 88% of the time you're having 0 deaths, right?
Mm-hmm. Correct.
And if you look at the original data, the probability of 0 deaths is only about 54%. So there's a mismatch there. So somewhere in the process of converting over to the binomial and then converting back, you're losing something. Because with 10,000 simulation runs, you shouldn't be that far off, and it looked like you were that far off each time. So so something's not right there, and I would love for you to send me your code, and maybe we can go through it together and see where. It's
it's in the assignment actually. Yeah.
Okay. So let me have a little bit of time to look at it first, and then let's talk about it. But this is actually a very useful concept of being able to reduce a more complicated case to something that you can simulate with a built-in function, and then simulate and then go back to what you were working with originally. So, if we have a Poisson distribution, there are built-in functions for that, but we might have a distribution that's not built into R. And so
and part of my I think part of my personal objective with this exercise was to kind of like understand, like bridge the gap between this lambda, this number. I was particularly puzzled by this. What is this 0.61 that's per corpse year? What the hell does that mean? And every time I look at see how this guy like partitioned the data to come up with this 0.61, I'm like,
so it's just the average. If you look year by year, it's the average number of deaths per year.
Yeah.
So per core per year. So
per core per year. But then my questions are becoming, what if you have varying corpse sizes? You know what I mean? What if you have a different sizes? So that's why I just started like
one of the
running down this rabbit hole to like reach the gaps there.
Yeah, so I think in theory your approach is sound. It's just somewhere in there the details are getting confused along the way. But but we can take a look at that and see if we can figure out where. But I do like the approach. It's just
numerical death per individual is 0.061. It's 6%.
Right.
Per individual.
Because there are 10 individuals in the core, so the expected value of total deaths in the core would be 0.61, 10 times that, right? But So, all right. Well, let's move on. But you and I can revisit that and maybe turn it into something pretty neat. Okay. So Shaker with 4.16. Are you ready to go? Let's see.
Yes, Mike, I can.
Okay. I'm making you presenter. So you should be able to share your screen and work through this.
Sure.
And we are right on the cusp of being out of time, so we'll run a little bit over. If you have to leave, this is being recorded. So please do feel free to do what you need to do. So go ahead whenever you're ready.
Yeah. So basically, this problem 4.16 is asking us to prove. It was given that x and y are independent random variables there. The problem is asking whether expected value of x by y is equal to expected value of x divided by expected value of y. So we have to either prove that, or we have to give some example, or some way to disprove that. So basically, as per the formula, expected value of any function here it's a multivariable function having x and y. So as per the formula, it is supposed to be f of x multiplied by the joint distribution of both the random variables. So x by y, and then here p x is equal to x and y is equal to y is the probability distribution of both the variables together. So since these x and y variables are independent random variables, the probability of x is equal to x and y is equal to y can be written as probability of x is equal to x multiplied by y is equal to y. So here, this is where I stopped, and then I evaluated the expected value of x divided by expected value of y. So here, it will be x multiplied by probability of x and then y multiplied by probability of y in the denominator. So both of these values are not equal. So I concluded that this cannot be expressed. Expected value of x by y cannot be expressed as expected value of x divided by expected value of y. I thought of giving some other examples such as rolling a die and tossing a coin. But here the proof is obvious, so I thought of using this method and to disprove that. So simple proof.
Okay. Yeah, it's often a matter of personal preference how to show something is false. In this case, there are a lot of simple counterexamples that you could find. I would argue that the proof is, from my perspective, the proof is much more difficult than just giving a simple counterexample. But that really is personal preference. So if you find this easier, if anybody finds this the easier approach, that's absolutely fine. One thing to be careful of, it's not a not equal sign, strictly speaking. It's not guaranteed to be equal to. Right? You can also find cases where the expected value of x divided by y is equal to the expected value of x divided by the expected value of y. So there are cases where it's true, but it's not always true. So
Okay.
So you gotta be careful about that, and you can see from what you've laid out here what conditions might have to be true to make it work, right? So you could start playing with, well, what would this have to be? What would that have to be in order to make this equation actually hold up? So there are cases where it works. There are cases where it doesn't. So in my mind, it's a really nitpicky detail of notation. It's not necessarily equal to would be the way to word it, right?
Could you give me one example where, if you can think of now, where the expected value of x by y, this is indeed, equal to expected value of x by y.
Boy, I go out on a limb and then I don't have one off the top of my head, but a simple.
Just an example. Yeah. Go ahead. Sorry.
Okay, I was going to say a simple example is where each random variable has just one possible value.
Yeah, or else if they have identical distributions, I'm just thinking about that. I'm not sure if they have identical distribution.
Right. So if you say x is a random variable that can only take on the value 1, and you say y is a random variable that can only take on the value of 2, then the expected value of x is always going to be 1. The expected value of y is going to be 2. And x divided by y is just 1 divided by 2 every time. So the expected value of x divided by y is going to be equal to 1/2, and the expected value of x is 1, the expected value of y is 2, which is also going to be 1/2. So they will be equal in that case. It's a really simple, trivial example of where they come out equal. And I'm sure if we put our minds to it, we could come up with a more complicated one, but that one works. So there is one where they are equal, but it's really so what you've shown is that, if I'm reading it correctly, is that they don't necessarily have to be equal, and that is what we're trying to show. So
Mike?
Yeah.
Kind of like on that similar thing, argument that you were proposing. I was thinking, but I don't know if like the support of that distribution kind of like throws the thing, reinforces the inequality of it. Because if it is valid, like let's just say that you have a single value, and the support of that distribution is just that one single value, and if you divide it over the other, then you end up with expected value of another value which has no support. You know what I mean? Which may not be a probability distribution function at all.
Well, but you just say the probability that x equals 1 is 1. There's your probability distribution function. The probability
but then if you end up x over y, but then if you divide it by, you have the other one over, but the other one is 2.
Well, you can imagine a table. So Brett has lamented the use of Word in doing these things. I'm going to do it anyway. So let me bring up I'm going to steal presentation back from you here, and let's see here. So to give you an idea of how this might work with some of the different examples you could take a look at. Okay, so let me insert a table here. I'll do a 2x2 first, right? So along the top we'll have the x values, and along the left column we'll have the y values. So you could have a 1 or a 2 for x and a 1 or a 2 for y, for instance. Right? So in the table here, I'm gonna do the x divided by y. So this is 1 divided by 1, which equals 1. Right? This is going to be 2 divided by 1, which equals 2. This is going to be 1 divided by 2, which equals 0.5. And then this is going to be 2 divided by 2, which equals 1. Right? And if they're independent, then we can just multiply the probability distributions for each row times each column to get the probability of each cell. Let's just make it easy and say in both cases it's 50-50. So then the probability of each of these 4 cells here that are the joint outcomes is 1/4, right? If we have a 1-by-1 table, these all go away. If we just say here, oh, I had it the other way around, x and y. So we just say x divided by y equals 0.5. Then the joint probability distribution table, now this cell has a probability of 1 because it's the only outcome, right? So it still has a probability distribution. The probability that you get x divided by y equals 1/2 is just equal to 1. And so we still satisfy independence, and we still have a proper probability distribution, and yet it is an example where the statement holds true. So so there are going to be cases where it holds true, and there are more complicated ones. I can't think of one off the top of my head, but that's a very simple example where it does hold true. So the way to read it is that it's not necessarily the case that the two things are equal.
So Mike, for the choice specifically, all I did is I just extended the expectation of x over y by saying is equal to the expectation of x times 1 over y, and I applied the independence rule, so I end up with something like expectation of x over y is equal to the expectation of x times the expectation of 1 over y. I just simplified it, and all I had to do is to prove is the 1 over the expectation of y is it equal to the expectation of 1 over y, and that's and I just presented an example that holds 4. Really, at the end, what it is, I extended the x over y to x times 1 over y, and I applied the expectation rule on those using the independence rule, and I end up with something like all I have to do is prove 1 over expectation of y is equal to the expectation of 1 over y. Mm-hmm. And they give an example of x squared and 1 over x, and then it did not hold true. So I'm not sure if it boils down to just prove 1 over expectation of y is equal to the expectation of y 1 over y. Is that what this really is? What this is about, or something else different?
It sounds like you're on the right track. I don't know. We'd have to sit down and look at it a little bit more closely. It really is a tricky thing to try and do algebraically to show that this doesn't work.
Yeah, right. I mean, I took the x over y, and then it says.
Yeah. What you're describing sounds. When I first tried the problem a long time ago, sounds like the first thing I tried to do. So. It sounds like you're on a reasonable track forward there. But in the interest of not keeping everybody here for too much longer, I think I'd be happy to sit down with you one-on-one and see if we can work through that. We know the right answer now too, because we've seen an example where it works and one where it doesn't, right? But
exactly right.
But yeah, by all means, reach out to me by email and we'll set up a time and see if we can make sense of what you're describing. I would be happy to do that.
No problem. Sure. Thank you.
Okay.
If you give me the presenter, I did the same way. So.
This is Nathan, right?
Yeah. Can I show you or not?
I'm making you presenter.
Okay. Thank you. Okay, this is I did that. Maybe this is the same thing he did. So I made this, and as you can see, suppose I put the 1 over y like this, and I changed it. So actually, the question is this: e and 1 over y equal 1 over ey. So e should be true. So I put this number, so it's not, the value is different, so it's not true I did like this. Is it okay?
Right, that's exactly what I did. You're right.
Yeah. So.
And I gave an example to prove that 1 over the expectation of y is not equal to the expectation of 1 over y. I gave an example
Right. Yeah, that'll do it too. Yeah. That'll definitely do it too.
Okay. I'll bring it back.
Okay. Okay, so we're well over time, but I think this has been a good session. Again, next Tuesday, during our normal meetup time at the normal meetup link, we'll hold. It's an optional session, but it'll be another session, problem solving. Please do show up if you're interested. I'd encourage you to take advantage of that. Most of you are also in 607, so he'll have the session for 607 earlier, just like normal, just like today. So please do take advantage of that. And reach out to me if you have questions, and let me know what I can do to help. Otherwise, I guess at this point I'll go ahead and end the meeting. We'll be looking for presenters for future sessions as well, so please do think about that and what you might want to present. And Derek, I know we didn't get to you. Maybe Tuesday next is the time for you to go. Would that work for you? Are you still here? Yeah, you're still here. Oh, you're muted though.
He's replying through the chat, Mike.
Okay, great. Yep. Yeah. So yeah, we're not too bootstrapping yet in the course anyway, so it's not going to kill us that it waits a week. But yeah, maybe, and we'll make sure we record it next week too, so that everybody can see it, even if you can't make the meetup. But why don't we lead off with that next time then?
Are you, Mike? Question.
Yeah.
Are you gonna post week 4's assignments anytime soon?
Yeah, those materials will go up tomorrow.
Okay.
So cool. Andy and I are working through the final details on that.
Mike, since we are kind of late on this course, would there be any revised syllabus for this? Would you be putting that in the website about the topics that you're going to cover?
So I can do an updated schedule, perhaps. We're still going to cover the same topics. The depth of some of the topics will change a little bit, but that's actually okay, because we're going to change a little bit the delivery method as well to try and make it a little bit more student user friendly. And so I think we're going to focus in on the parts of those topics that are most essential for data science. So that at the end of the semester we can honestly say you've got what you need to have from the course going forward. And there are a few things that are fascinating to somebody like me who often lives in the theoretical statistics world that you just don't need for data science, and some of those things we'll mention them and they'll be covered briefly, but we won't go in quite the same depth. So those are the things that'll go more than anything else. But we'll have plenty of time to cover the essentials.
Okay, thank you.
Okay, so I think at this point we'll adjourn until next week, and please reach out to me if you have any questions. Yep. Good night, everyone.
All right, Mike. Thank you.
Bye, Mike. Thank you.